Okay, so this one is the latest physics paper, February-March 2023. So question 1. A student determines the diameter of a marble by 2 methods and calculates the density of the material from which the marble is made. Should be very straightforward, this question. So we are given some information about the marbles. So we are measuring 5 marbles at a time. So we are measuring the total length of the 5 marbles. So first question, figure 1.1, measure the length D. So this part is very straightforward. So we will take the ruler and then measure the total distance. So if we were to print out the paper in full size A4, we measure accordingly, we should get 7.8 cm. So straightforward. Next question. Use your value of D, calculate the average diameter of one marble. So this part is also very straightforward. So we can see that the D that we are measuring is for 5 marbles. So we already know total 5 marbles is 7.8 cm. So we take 7.8 divided by 5. So that will give us one marble approximately 1.6 cm, the diameter. Straightforward. Okay, next question. Suggest why it is more accurate when using a ruler to measure the diameter for 5 marbles rather than measure the diameter of a single marble. So we are measuring the total distance of 5 marbles and then divided by 5 instead of just measuring one marble. Why is it better to measure 5 marbles at a time? So straightforward, because the effect of uncertainties will be reduced, or the diameters of marbles might vary. Okay, so each marble might be having a slightly different size. So if we measure 5 marbles, we can get the average, which will be more accurate. So the idea for the effect of uncertainties. So the idea of uncertainty is that, let's say we use the ruler, the smallest scale of the ruler will be 0.1 cm. So the smallest scale that we can measure is 0.1 cm. So the uncertainty will be half of this. So we cannot tell the difference between 0.05 cm. So let's say we measure one marble. So if we were to measure one marble, the reading will be around 1.6 cm. So the total will be around 1.6 cm. So our percentage uncertainty for one marble will be 0.05 divided by the total 1.6 multiply 100%. So that will give us 0.05 divided by 1.6 multiply 100. So this is around 3.1% of uncertainty. So for any measurement, we want as low as possible the uncertainty. So if we have a large uncertainty, we are not sure about our measurement. So we want to have as low as possible. So if we measure 5 marbles, so the total is 7.8 cm. So the percentage uncertainty for 5 marbles will be 0.05. So we're still using the same ruler, still is 0.05. But now the total is 7.8. Okay, 0.05 divided by 7.8. So now the uncertainty is 0.64%. So it is lower. So it is telling us that if we can, it's better to do more measurement at a time. It will decrease the uncertainties, which will make us more confident of our measurement. So these two possible answers, effect of uncertainties will be reduced, or we want to take into account the small differences of diameters between the marbles. Next question. So figure show two wooden blocks, one and one of the marbles. Describe how the students uses the two blocks and the marble to determine a new accurate value for the diameter of a marble. Draw a diagram to show the arrangement. Describe clearly how the student ensures that the value of the diameter is as accurate as possible. Just now, our measurement, we were not using the wooden blocks, so we measure straight away. So if we use the wooden blocks, we can get a more accurate measurements. Okay, how do we set up the measurement? So it should be something like this. So we can set it up like this. So we put the marble in between the two blocks and then we measure accordingly. So that's the idea. So if we just measuring one marble, so we can use the wooden block, which will be more accurate. So we can see the boundary more clearly. So this is the diagram, so that will give us some points. Describe how to ensure the value as accurate as possible. So how can we ensure as accurate as possible? Yeah. So first, use marble between two blocks and measure the gap. So this is the first point. Secondly, we will measure the gap as at least two places. So we will measure one at here, and then we will measure another one at here, for example. Okay, or we can measure another one at here. So we measure at different position at the block and get the average. Make sure we get as accurate as possible. Yeah. And then another possible answer, rotate marble to different axes to take average of measurements. Okay, so these are the possible answers for this question. Next part. So student uses the top pen balance. So here we are measuring mass. Top pen balance to measure the mass of the 5 marbles. He measures the mass of the beaker, empty beaker, without the marbles, and then measures the mass M5, same beaker containing the marbles. So this question is very straightforward. We want to record the values M0 and M5 as shown as the top balance. So this will be the M0, the mass of the empty beaker. And then here will be M5, beaker plus the marbles. So we take the readings and then we record. Straightforward. Use these values to calculate average mass of one marble. So what do we do? So we take the total M5 minus the beaker, the mass of the beaker. So that will give us the mass of the 5 marbles divided by 5. So that will give us the mass of one marble. The student pours water into a measuring cylinder, records. So we know that for density, we need mass over volume. So up to this point, we already have the information about the mass. So next, we're going to work out the information about the volume. So he records the reading V1 of the water level in the measuring cylinder. So we're going to take the reading before and after we put the marbles. So the before reading is 26 cm cube. So now, after we put the marbles, we have the after reading. So we will take this reading here. So straightforward, 38 cm cube. So record the new reading will be 38 cm cube. Calculate the value of average volume for one marble. So this is very straightforward. So we will take just now, after we put the marbles and before we put the marbles. So that will give us the volume of the marbles divided by 5 marbles. So we will get volume of 1 marble. So now we already have information and volume for the marble. So we can calculate the density. So mass just now, 6.7 for 1 marble. Volume, 2.4 for 1 marble. So that will give us approximately 2.8 grams per cm cube. Describe one possible source of inaccuracy in the method described and suggest one improvement to reduce its effect. Looking back to our experimental method, okay, what can we identify as possible source of inaccuracy? Example, graduations on measuring cylinder is too large. So here, the graduation is the smaller scale will be 1 cm cube. So this may be too inaccurate because we cannot differentiate less than. So the uncertainty will be 0.5 cm cube. So if the change in volume is less than 0.5, we cannot identify that. So we need a measuring cylinder with higher accuracy. So for example, let's say the smallest scale will be 0.1 cm cube. So we can get uncertainty of 0.05, which is much more accurate. So we can change another measuring cylinder. How to improve? Use a smaller measuring cylinder or greater number of marbles. Okay, another thing that we can do, we can use more marbles. So we are getting a bigger number. So again, our uncertainty will decrease. Next question. So this is a thermal topic question. Student investigate cooling of hot water from different initial temperature. So yes, so this is our setup here, straightforward. So we have the beaker, we have the thermometer. So what do? We pour the water into the beaker and then we measure the cooling process. So first question, student measures the room temperature. Record room temperature as shown in thermometer. This is very straightforward. We take the reading here, which is 21 degrees Celsius, straightforward. Describe one precaution that students take to ensure this temperature reading is as accurate as possible. So one of the key things when reading the thermometer scale will be wheel scale perpendicularly, straightforward. So we want to read the scale at a right angle, okay, perpendicularly. So we are doing 2 experiments here, experiment A and experiment B. Student pours a volume of 100 cm cube of hot water into the beaker and then record the temperature. initial temperature at time equals to 0, and then records the temperature of water every 30 seconds. So we have some results here. So we are taking temperature readings from 0 to 180 seconds. So straightforward, what we expected. As time goes on, the temperature will be decreasing because we are cooling towards the room temperature. Very straightforward. Then student repeat the process. She wait until the initial temperature of the water is same value as the temperature theta A at 90 seconds in experiment A. In the first line of table 2.1, record her initial temperature delta B. So what we want to do is we want to work up this initial temperature. So the key word we need to pay attention is this initial temperature for experiment B. It should be same as experiment A. But same as experiment A is not at the 0. It's same as 90. So we want same as experiment A, but at 90 seconds. So which means we want to control the initial temperature for experiment B at 85. So that is the idea for this question. So our answer here, it will be 85. So that's the idea. All right. Okay. So next question. Write a conclusion stating how the temperature at T0 affects the rate of cooling of the water. So we can take a look at the results here. Justify your answer with reference to the values from the results. So what will be our conclusion? So first thing we can see, for both experiments, as time going on, the temperature will be decreasing. So how about if we compare experiment A to experiment B? So what we can see here, what is the main difference? The main difference in initial temperature. When initial temperature different, the final temperature also different. So another main thing we look at, how much the temperature has dropped over the same period of time. So that is related to the rate of cooling. So essentially, we can see that when the initial temperature is lower, the final temperature is also, the rate of cooling is slower. So here we have 92 to 80. So it's dropped by 12 degrees Celsius. So from 85 to 75, it only dropped by 10 degrees Celsius. So we can see that when we have different higher initial temperature, the rate of cooling will be faster. So this is the statement that we can give. The higher the initial temperature, the faster the rate of cooling. So this is our conclusion. Secondly, we need to give reference to the values in the result. So how do we give reference? So we can say that experiment A has higher initial temperature of 92 degrees Celsius, which dropped to 80 degrees over 180 seconds, from 92 to 80. For experiment B, initial temperature 85 to 75. Over the same period of time, which shows a slower, sorry about that, a slower cooling rate. Yeah, so experiment B will be slower cooling rate. Yeah, so basically For statement matching, so what we need to answer. So according to marking scheme, what we need to answer, statement matching readings in the table. And then comparison of changes over 180 seconds. So next is a calculation problem. So calculate the average cooling rate X1 during the second half of experiment A. So what I'll do, I will copy the table. So we need to pay close attention on the question. So what is asking for? So calculate average cooling rate for X1 during the second half of experiment A. So we only want second half of experiment A from 90 seconds to 180 seconds. So we will focus on this part. So the temperature at 90 and the temperature at 180. So divided by the time, which is 90 seconds. So pay close attention to that. So 85 minus 80 divided by 90. So that gives us a cooling rate of 0.056 degrees Celsius per second. Yes. Okay. So we need to be careful. So instead of using the first number, not that. So we need to read the question carefully. Use the data that it is asking for. So second question, also pay close attention. So for the second calculation, we want the first half of experiment B. First half of experiment B. So temperature at 0 and temperature at 90. So divided by the time, 90 seconds. So 85 minus 79.5 divided by 90. So that gives us 0.061 degrees Celsius per second. So yeah, so these are the results we have so far. All right. Okay, so we already have the two answers. Right? So now we will see carefully what we are comparing here. So the first calculation, we are calculating this part. Second calculation, we are calculating this part. Okay? So actually it's very similar calculation. It's going from 85 to 80. So it's 5-degree difference over 90 seconds. So this one is also very similar. So this one is 5.5 degrees Celsius over 90 seconds. So we can see here, this is very, very similar calculation. So we expect them to be almost similar. So in fact, we have very similar answer. So just now, this X1, so this is X2. So just now X1 is 0.056 degrees Celsius per second. So we know that here we are calculating essentially the same thing. So we expect them to be very similar. A student suggests that X1 and X2 should be the same. State whether your results support this suggestion. Justify your statement by reference to your result. So what can we say here? We can see that they are quite close. So we need to do some calculations to confirm. So first, our statement will be yes. So we can say that they are quite close. So how do we justify that? So we will do the calculations. So if we do the calculation, percentage difference, how much difference? 0.061 minus 0.056 divided by 0.056. So we can see the difference is 9.1%, the difference. So if we look at the difference between the two values is less than 10%, which is within the limits of experimental accuracy. So we can say that the difference is less than 10%, we can say that they are the same within the limits of experimental accuracy. Next question. State two variables which must be controlled so that the comparison of x1 and x2 is valid. So we know that for each experiment that we do, we only change one parameter at a time. We only change one variable at a time. So we are not changing 2 or 3 variables so that we can compare the experiments fairly. So in this case, we are only changing one variable, which is the initial temperature of the water. We are not changing anything else so that our experiments are comparable. So this is the independent variable, and the dependent variable will be the cooling rate, how fast it is cooling down. So we know that when we change the initial temperature, the cooling rate is also slowing down. So which means everything else we need to keep constant. So for example, same volume of water, we must use same volume of water, same beaker, same material, thickness, surface area, and shape, because this will affect the rate of cooling as well. Same room temperature. Yes, so these are the main things we need to keep constant. Next question. So this one is about the electrical system. Student investigate the properties of a resistance wire. Straightforward. So we have power supply, and then we have ammeter to measure the current, and then we have the resistance wire that we want to measure. So basically, we will place the crocodile clip at different positions. Then it will give us a series of current measurement and also the potential difference measurements, which we can use to work out the resistance. So straightforward. First question. On figure 3.1, draw a voltmeter connected to measure the potential difference across the length of the resistance wire. So we already know the ammeter should be connected in series with the experimental setup. How about the voltmeter? So the voltmeter should be connected in parallel. So the voltmeter should be connected as such to measure the potential difference across the wire. Next, so we are having some reading here. Student connect the crocodile clip at 20 cm of the resistant wire. So let's say our first measurement is maybe somewhere here, 20 cm. So we can get a current reading and a voltmeter reading. So, and then after that, we will change to different position and then take the readings accordingly. So our first set of reading, read and record the first line of the table 1, the values of V and I shown on the meters. So this is straightforward. So we can see here, this is 1.3 for the voltage, and then for the current will be 0.86 ampere. Very straightforward. So, and then repeat the process for different length. Yeah. So repeat the process at different length of the wire. So this is the table that we will get. So voltage 1.3, current 0.86. Next question. For this set here, calculate the resistance. Straightforward. So V over I. So the answer will be this. V over Y, so that gives us 1.5. So this is the result we will insert in the table. And then next we can plot the graph. Resistance versus the length. So the points we need to pay attention when plotting a graph. So first, we label the axis. Resistance versus the length. Label the axis with the unit. Secondly, we will set up the scales for the y-axis and x-axis. So x-axis is this. So from 20 to 100. So the suitable scale will be 0, 20, 40, 60, 80, 100. And then resistance, we are going from 0 to 8. 0 to 8, so we can use this scale here, 2, 4, 6, 8. Straightforward. And then we plot each point accordingly for the x-axis and the y coordinate. Straightforward. And then draw the straight line of best fit. So the straight line of best fit will be somewhere in between all of the points. So this will be our plot. So next step, determine the gradient G. Show clearly how you obtain. So what we do, we define a triangle. So it can be any triangle. So we try to take the triangle that is as large as possible. So it gives a more accurate calculation. So the gradient will be difference in y divided by difference in x. So that will be our gradient. So difference in the y axis and divided difference on the x-axis. So the gradient. So we calculate accordingly. So finally, that gives us 0.081 ohm per cm. So that's the gradient that we have. Yeah. So next step, the gradient is numerically equal to the resistance per unit length. So write down the R naught. So we already given that this R naught is numerically equal. So what do we do? Essentially, it's the same. So in the marking scheme, so all of these answers within this range will be acceptable. Next, suggest one practical reason why students carrying out this experiment may not obtain the same readings as in table 3.1. Assume that the procedure has been done carefully. So what would be some possible problems that we can encounter that causes the readings to be not very reproducible? For example, inherent source of accuracy, difficult to position the crocodile clip accurately as exactly the correct position, inconsistent connection with crocodile clip, resistance of wire is not uniform. So maybe the wire, the diameter is not the same everywhere. So that can have some effect on the resistance as well. Final question. So final question, it is about designing the experiment. So based on the information given, so we can look at the picture. So this is the picture here. A student investigate the motion of a ball through the air. Plan an experiment which will enable him to investigate how the range of the ball depends on the angle at which it is launched. So basically, we will put the ball here into this channel. And then what do? We will adjust this angle. So this angle, it can be like this, or it can be like this. So we can adjust the angle for the end of the channel. So when the ball come out, it can come out like this, and then it will start rolling on the ground. So depends on what angle it comes down, it can affect how many cm it can move. Yeah, so it depends on at which angle it falls down, it can affect how far it will travel after it falls down. So that is the main point. The range is the horizontal distance that the ball travels after leaving the end of the channel shown before hitting the ground. So apparatus available. So what we have so far, a flexible channel. So this is what we have, which can be bent at different angles, a selection of balls, each of different diameter and mass. So in your plan, so these are the 5 points. So in our answer, we should give answers to these 5 points to get the marks. List any additional apparatus, explain briefly how to do the experiment, state the key variables to keep constant, draw a table to show how to display the reading, explain how to use the result to reach a conclusion. Okay, so first point, list any additional apparatus. So what else do we need? So we already have the flexible channel. We already have the ball. Next, we need the meter ruler to measure the range. After the ball has fallen down, how far it travels. So we need the meter ruler and protractor to measure the angle. Okay. So at what angle the channel? Okay. What is the angle of the channel? We need the protractor. Second question, how to do the experiment? So this part is straightforward. So we can get the points here. So for this question, the total points will be 7 points. So finally, our answer, we will write more than 7 key points. So we try to write as much as possible so we can get the full marks. So the step straightforward. Step initial launch angle. So first we adjust which angle we want. Let's say we want it at 20 degrees. So we set the angle. We roll the ball, put inside the channel, let it go. And then after it fall down, it will, let's say it stopped at here. Then we will measure the range. So the 3 main steps here. Next part, state the key variables to keep constant. So we are only changing the angle. So everything else will keep the same. So some examples of the answers that we can give. So anyone, diameter of the ball, we must be using the same ball each time. The mass of the ball, the angle or height of the upper end of the channel. So this part here should be constant. Next, draw the table with column headings. So what will be the suitable table to draw? So first, we must have the independent variable, which is the angle, at which angle that we launch. Okay, the angle that we are adjusting here, and the range. So how far it will roll after it falls down from the channel. So this is the dependent. Okay, so what we are measuring and what is the unit. So we include this. Finally, Explain how to use the result to reach a conclusion. So what will be our analysis? How we analyze the result? Yes. So table with columns for independent variable and dependent variable. So this one. Compare the readings in the table to see if a change in independent variable produce a change in dependent variable. So, or another way to analyze, plot a line graph. Finally, we can also have some additional points, anyone that can give us some additional marks. For example, we can say at least 5 sets of data taken. So we are doing maybe at least 5 angles. Okay. Repeat each measurements and take average. So for each angle that we do, we will take maybe 2 or 3 times repeat. Means of accurate indication of point at which ball hits the floor. So how do we know where the ball hits the floor? So we need to maybe quickly mark down the position as soon as possible. Clear indication where to measure the range from. So this will be the points that we can include. So with this, we finish the whole paper.